Hi and welcome to the logarithmic functions lesson for today's lesson where I'm missing. Just to give you a little bit of a heads up on what you need to know about log functions, help you a little bit with your assignment, and obviously I'll be back in the following lesson and I'll give you some time to practice and ask me questions then. So let's start with our standard. Remember, our standard transformational form is that a function of x is transformed as a f of bx minus c plus d, or it could be a function of x is transformed as a f of b and then x minus c. And I don't actually need that first bracket, so I'll just take that one off, plus d. So either of those two forms is transformational form, and this one you'll see is more common in that trig function area, and this one's common in the quadratic functions and areas like that. But you remember that I've spoken to you about the fact that we don't always need a, b, c and d. So I'm going to start by saying that we'll typically head towards that form for our logarithms, and I'm going to write down our standard log form as f of x equals a log base, let's just come up with, say, x. Oh no, it can't be because it's f of x, z, and then b x minus c plus d. So I've chosen z as our base, but we'll probably head towards having a base of e in most situations. And z could be any number, and z really is inconsequential for this part of the lesson. But I just want to show you how the b is not really important, and we'll probably stick with the a, c and d as our standard transformations. We don't have to worry about that transformation b. So let's look at y. If I do one of the log laws here, I can write this down as a and then log base z of b plus log base z of x minus c. And so you notice here that I've just done that one, the log base x of ab is equal to log base x of a plus log base x of b. That's one of our log laws. So I've split that product here between those two terms. I'll split that up into two pieces with an addition in between using that log law. Now if I expand this, I get a log base z of b plus a log base z of x minus c plus d, and rearrange it, and I get a log base z of x minus c plus a log base z of b plus d. And now we have, obviously, our variable is x, and all the rest of the letters apart from the log are just unknown constants that we can work with in different ways. So that means that this term here at the end, well, that's just a single constant. So I can write that down as d as well. Let's just call it d1, or it might be c in some contents. But either way, that is just a constant, so I can write that down as just a constant. So if we have a b value in our log, it actually forms part of our d value. And I'll show you a little bit why that is in a second. But let's just start by writing this down now as log a log base z, whatever our base is, x minus c, so I didn't need that second bracket again, plus d. And I'll show you very quickly. We just shoot along here to my open Desmos file, and you'll see that I've set this up already with sliders for a, b, c and d. And my slider here for a is at 1.10. I'll just move that back to 1. B, I'll move back to 1. C, I'll just move back to 1 as well. And D. Now, there's our standard log function, which I'll just shift across here. And that standard log function can be transformed using these. But have a look at D. D does what we expect. That constant on in always just shifts it up and down. Now, if I move D back to 1, have a look at B. B, now it's negated it when B is negative, but when it's positive, what's it doing? It's just shifting it up and down. Now it's shifting up and down not quite like D is, because it's a log base Z of B, but it is still shifting it up and down. And just out of interest, so you know, this log with nothing here, that means log base 10. So this is working base 10 at the moment. So B is doing the same thing as D. And if B is negative, there's a slight change, but ultimately it's still just D with a different transformation. So we're going to work without our B. And I'm going to just change that A to try and get a bit nicer shape here. You can see A is that dilation factor, and C you can see just moves along the horizontal axis as we expect, because that's what C does usually. And we can take a screenshot of this so that we've got that in our OneNote file. And so let me just change this. There we go. So here's our screenshot, and I can use that to talk about it. So just going back to our OneNote file here. So there's our log function with our f of x and our x here. Now there's a few important features of a log function. So all of our log functions will have a vertical asymptote. In this case, it goes quite quickly towards that asymptote, and that asymptote is 1. Now that's just special because of the function we've chosen. So let me just show you what that means. If I go back to this Desmos file and go down, you'll see that it's getting closer and closer to 1, but it will never actually quite reach 1. Now the reason why it's 1, it's not typically 1. A standard log function won't be 1. The reason why it's 1 is I've set my C value as 1. So if I just scoot C along here to 0, you'll see now that the asymptote is 0. So when there's no C value, so for our standard log function, which I'll draw here as, I'll do it in green, as f of x just equals log of x, well, it will come up right next to that x-axis here. And it will do a very similar thing to this one and shoot along like that. It has an asymptote here of 0. So just remember this word if you haven't seen it before, asymptote. And that is a line that the function will head towards, getting closer and closer and closer, but never quite reach it. You'll also remember that log functions and exponential functions are opposite functions. They negate each other in a way. And it's interesting here that exponential functions have a single asymptote that is horizontal, and log functions have a single asymptote that is vertical. So you get that nice reflective property. Now it's easy to fall into the trap of thinking that a log function looks a bit like it's got a horizontal asymptote up here somewhere as well. So I could just, I'll just change the size of it. It looks a bit like that, but it will never have that. It's just slowing down in growth. So I just go along here again. You see it keeps on growing, but it's just the rate that it's growing is getting slower and slower and slower. But it will go to infinity eventually. So there is no horizontal asymptote, there is a vertical asymptote, and that vertical asymptote is based on the C value. So we can write that down here. C value is equal to the vertical asymptote. And of course, the D value will just do a shift vertically, but there's not a lot I can tell you about the D value, except that it's a shift vertically, because whilst it shifts it up and down, it really depends on the A and the C value on how it affects, say, our x-intercept, or how it might affect the height that it's getting to here, you know, at 10 or 15. That A and that C value have a fair bit to play in that as well. And our A value, of course, is a dilation. And, you know, we've done this initially working with quadratics and periodic functions, and the A value is really nice in those functions. The A value in a quadratic, it draws it from that turning point, and a periodic function, it draws it from that center of motion and represents the amplitude. In a log function, it's not so nice. The A value does enlarge it. You can see that sort of stretch happening there, but it's happening in both axes. It looks a bit unpredictable, so it's not a great deal you can do with that. The trick here, though, is to be able to recognize and find your vertical asymptote, and also how a log function transforms and moves, some of the important points you get, you know, how we can represent our x-axes, etc., etc. And a lot of that's going to come from playing with log functions. But the key will be you developing a way to represent or find a log function, probably because you will want to be doing some differentiation, perhaps a log function base e, log base e, which can also be written as ln, the natural log. Probably base e, you want a log function that goes between two known points for your assignment. So the two known points might be 3, 7 and 4,8.5 or something, and how you can work with that. And again, you're looking for those key points. So you might know something about a standard log function, like for example, it's x-intercept. And so the standard log function, f of x equals log x. If you let f of x equals 0 to find the x-intercept and rearrange that, you'll get x is equal to 1. So our standard log function has an x-intercept of 1. So you can use c and d values to get our 3 and 7. So it starts at 1, 0. We know that as our standard log function. And if you do a c transformation, which is the horizontal transformation such that c is equal to 2, it was shifted along from 1 to 3. And if you do a d transformation such that d is equal to 7, it will shift it up by 7, so that now it's going along, or so up to 7, you get your 3, 7 starting point. And then you need to work out how to play with your a value to get your 4, 8.5. You work through that worksheet that's on here and just play around with finding your vertical asymptotes, finding important transformations that are happening. You'll get a better idea of what's going on there. In your assignment, you really want to try and explain the transformations that are going on as much as possible. Anyway, I hope that's helped, and all the best.